All right, today, big day. We're going to get serious with some series. All right, so we've been talking about sequences. Sequences are nothing more than a list of numbers. Great. Now we may want to add those numbers, maybe the first 3 terms, the first 5 terms, or the first infinite number of terms. Is that possible? We'll get there. All right, a series is the sum of the terms of a sequence. That's all there is to it. We can write it like this. Use a capital S. This means the sum of the first n terms. So if we had an S sub 3, it would mean the sum of the first 3 terms. We've used u sub 1, u sub 2, and so forth as the terms. And then the nth term is that last term or the nth term. All right. That's it. So in this section we introduce, this is purely notation. There is no, we're not moving on, we're not setting it up for another sequence or another series or formula. We're just saying we're going to use this sigma notation and we're going to rewrite instead of having to add all these addition signs. All right, so it is called sigma notation, sometimes called summation notation. Same thing. There it is. So we're going to rewrite a bunch of terms. So if we had this and we're like, gosh, I don't want to write all those terms, we use this notation. And there's a lot going on here. What you should be familiar with is this idea of u sub k. Okay, wait a minute, Mr. Sayre, it's always been u sub n. Well, they just changed the variable. So just think of this as our general term. This is what we call the dummy variable. In this case, it's a k. We'll use k all day today, but understand that I could have an I, a j, any letter under there that is going to take values. Well, what values does it take? Well, here it's signifying that it's going to start at 1 and it's increase by one integer or a whole integer every time. So then k will take 2, then 3, then 4, all the way up to this last value. Sometimes in general we'll put an n there, and sometimes we'll just put a number. I'll show you plenty of examples so that you feel comfortable with that. So how do you read this? How do you read this? Let's get rid of that. So this symbol is read the sum of all numbers of the form u sub k. So in other words, we'll get all these terms from this general term, and we get those terms by plugging in k equal to 1, k equal to 2, k equal to 3, all the way up to n. All right. Let's expand and evaluate. So here we are. We have our first sigma notation. This right here is our explicit formula. And sometimes it's arithmetic, sometimes it's geometric, and sometimes it's neither. Doesn't matter. But that is the formula that we're plugging the k values into. So here we're going to plug in k equal to 1, and then we're going to plug in k equal to 2, and so forth all the way up to 7. So that looks like this. So I've highlighted in blue the k value as it takes on its integer values. So when k equals 1, we plug it in and we get the value 1 plus 1. Sure, I could have written 2, but I wanted you to see that I'm taking each term and then adding it to the next term. Okay, so now k equals 2, k equals 3, k equals 4, and so forth. If we evaluate 1 plus 1, 2, 3, all the way up to 8, and then we can add it up. So when we say expand and evaluate, all we're saying is plug in those k values and then evaluate and see what it is. All right, I'll bring your attention to this one. That is neither arithmetic or geometric. I lied. It's geometric. Okay, so we're going to take values from k equal to 1 to 5. 1 to 5. Let's see what that looks like. So our idea is we start with k equal to 1, we get a term, and then we add the next term. And k equals 2, k equals 3, so forth. I hope the blue has kind of shown you what I'm thinking about as I write each term. That's the k value starting from the lowest and going to the highest. So 1 is usually the starting point, but I'm just saying k will start there and it'll go to the last value. I added those up in my head. I think it's 31/32. I hope it is. All right, so that's the idea about plugging in the k values to expand the series, create the series, all the addition of the terms, and then evaluate just means add them all up. All right, so what if we're asked to, you're given a series. A series, remember, is a sequence of numbers that are being added together, and we want to write the sigma notation. So this is what we want. Well, what do we have to figure out? Well, we got to figure out the general term, and we got to figure out how many terms there are. All right, general term. We just went through a whole thing about arithmetic and geometric. I'll explain if it's neither here in a second. So we go get it by using our one and only arithmetic formula. We plug it in, and we get our general term. But this has always been u sub k. Well, it doesn't matter if it's n or k, you just change and use k instead of n. That's no big deal. All right. The number of terms, well, you can count. I know you can. There's first term, second term, third term, fourth term. So there's 4 terms. Now that's pretty darn easy. So in this example, I did it 2 ways. One, you can count them. Great, there are 4 terms. But sometimes you're just given the last term and you don't really know how many terms it took to get there. So I'm just planting the seed that we have the general form, right? We have the general form. We have the last term. So if we set those equal, we can see what term number it is. We can see what term number is. And it should be 4, and it is. So when you write this in sigma notation, all you're doing is substituting in your general form, and you figured out how many terms there are. That's it. That's all there's to it. Let's do another example. 2/6/1854. I'll stop there. You might recognize this as geometric. So I start with the geometric general term. I plug in the first term. I plug in the constant ratio. Notice I've moved from n to k. Yep, that's just a formality. I know there are 4 terms. So I start out with k equal to 1. It's always easier when you write these that just start out with k equal 1. There are some advantages of picking different values. We're not there yet. Number of terms, obviously, and the general term. All right. All right, so we have the sequence. Notice it's not a series. It's 1, 3, 5, and so forth. So it's just a sequence. Write down an expression for s sub n using sigma notation. So now it's saying, hey, the expression s sub n is more of a series. So that's more like 1 plus 3 plus 5 plus 7. All right. And then part B, actually find the sum of the first term. The sum of the first 2 terms, the sum of the first 3 terms. All right, let's try it. Part A, can we write this in sigma notation? All right, we will please notice that 1357 is arithmetic. So we start with the general formula. There's only 2 formulas that you got to know, arithmetic and geometric right now. We plug in our first term and our constant difference. Notice I've moved from n to k, no big deal. I multiply it all out, and I have my general form. If you want to test it, maybe plug in a 3. 2 times 3 is 6, minus 1 is 5. Is 5 the third term? And it is. Okay, so now we have our general term. Notice this thing kept going, 1, 3, 5, 7, dot, dot, dot. That means we don't know how many terms we're adding, so we keep this as just a variable. And we use n to signify the nth term. We use k here to be that dummy variable that takes on k equals 1, so we plug it in and we get 1. K equal to 2, plug it in, we get 3. Plug k equal to 3 in, we get 5, and so forth. All right. What they're asking for is purely notation at this stage. For part B, find the sum of the first 1 terms. That's what S sub 1, it's ridiculous, it's weird, but it'll cause more trouble than most. The sum of the first 1 term is just the first term by itself. It happens to be 1 in this case. The sum of the first 2 terms, 1 plus the second term, which is 3, gives us 4. Sum of the first 3 terms, 1, 3, 5, and so forth. You may or may not recognize a pattern at this stage. It's not that important, but I will say it might have something to do with number 8 in your homework. This is for your notes only. What I mean by that is this is not something that we're going to kind of use too much right now, but I think it's important to have. And so when we reference it later, you can say, oh, I started kicking that around. You can pause it and write that down. All right. Now this one's kind of a tricky one. So I don't even know where to put myself here. I'll just swing, go down here in the corner, I guess. Let's do one thing at a time. So I wouldn't do this, but we did ask you to do number 7, which basically is this problem with a different expression. So we're going to walk you through it. First of all, we want to expand, oh boy, we want to expand this series, and that means plug in 1, plug in 2, and so forth. And then write it in reverse order. So we're going to expand it, then we're going to write it underneath in reverse order. I know, I'm glad I'm doing this for you. Second part is once they're written, then we're going to add them. But let's do first things first. All right. When we expand, what we do is we plug in k equal to 1, k equal to 2, k equal to 3, and usually the top number is a number, so we go until we get that number. But here we have to go till n. Well, I don't know when to stop. Well, we stop when we plug in n. So this is you should be able to see if I plug in n for k, I get 2n. But just to kind of show you that you get there, the term before n is the n minus 1th term, and the term before that would be the n minus 2. And the term before that would be n minus 3. So the dot, dot, dot kind of covers all of that. So that's new to you, and it's just a formality, and it's just notation. All right. I'm going to clean it up just a little bit. So 2 times 1, obviously 2, 4, 6. If I multiply this out, I get 2n minus 4, 2n minus 2, and 2n. And that makes a lot of sense, right? Because as we're moving along this sequence, we're adding 2 every time. So that we add 2 to that, we add 2 to that, and we get to that last term. Cool. All right. Now remind you of the instructions. It said expand it. So we have expanded it. Now reverse that order and write it underneath. So reversing the order means I start with this term and then I write this term and write this term, dot, 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 and so forth. So hopefully you can see that I've done that. All right, to continue that now, it said add vertically. So when we add vertically, we're adding this term to this term, and I get 2n plus 2. When I add this term to this term, 2n minus 2 plus 4. I get 2n plus 2. And you'll find that every vertical thing I do, I will get the same thing as 2n plus 2. So that's kind of remarkable. Now on this side, I have this sigma notation plus this sigma notation, means I have 2 of those sigma notations. Well, how many of those terms do I have? Well, there's n terms. So I'm going to have n of these. So n times 2n plus 2. Hopefully you can see I factored out the 2 because it's here and here. And remember, it's 2 times this equals 2n times n plus 1. I'm going to divide both sides by 2. And I end up with this. I say it's cool. You have no idea what's so cool about it. It's kind of a formula that allows me to find the summation of a bunch of terms that all have this in common. Let me show you an example. So this is what we ended up with. What if n equals 5? What if I wanted to find the sum of the first 5 terms? The sum of the first 5 terms. Well, I plug in k equals 1, 2, 3, 4, 5, get a bunch of numbers, add them all up, and I get 30. Awesome. Well, or I can use my cool little formula. And the formula says if I want to find the sum of the first n terms, I just plug in n into this formula. So if n equals 5, I plug in n equals 5, 5 plus 1 is 6, multiply it out, and I get 30. So all of a sudden, this series got a little bit easier to evaluate. Now, this is by no means something that you're supposed to just grasp, I got it. We want to hold your hand. We're giving you this example. We're asking you to do it 1, maybe 2 more times and go through the motions. All right? This is something that people will struggle and really create some amazing series later on. These formulas are really the art of it. So there are some famous series, and this is the one we basically just did, and in number 7 you're going to be asked to prove or go through that process, and hopefully you get that. There's also some for k squared and k cubed. In other words, if I wanted to add 1 squared plus 2 squared plus 3 squared plus 4 squared all the way to n squared, I can plug in. Now I'm not going to tell you that one right now because I want to evaluate it with you or show you kind of the process, but I want you to know that people reference these. They don't memorize them. They have a little reference sheet and they use these all the time. All right, your homework looks like this, and I just wanted to kind of say that I wrote a few things in the homework to kind of help you a little bit, maybe give you a head start on what they actually mean here. Is it that easy? Yeah. I said read. What I mean by that is, what is s of 4 equal to 13? When you read it, it's the sum of the first 4 terms equals 13. And the sum of the first 5 terms equals 20. With that information, can you figure out the 5th term? Maybe. Number 3 is a lot like the examples. Number 4, a lot like the examples. 5, I'm sure you can try to figure that one out. 7 is just like our example with rewriting the order. I didn't ask you to see, but if you want a challenge and you want to put a few things together, you're certainly welcome to try it. And 8 is a lot like 7. All right, we kept it under 20. Really important for the notation aspect that you understand what sigma kind of holds and does for you. All right, we'll see you tomorrow.